the acceleration of the elevator when it is speeding up. In this graph, we are going to be using trial number 3 as an example of the calculations that we used to find the acceleration of the elevator. This is trial 3, as you can see by this point over here. So to get the acceleration, all you have to do is divide the force by the mass. In trial number 3, the net force, was 0.5 newtons. And the mass was 0.97 kilograms. This is the standard formula for Newton's second law. So what we do is isolate the acceleration by dividing 0.97 in both sides. And presto! We get the acceleration of the elevator when it is speeding up, which is 0.515 meters per second squared. This is finding the acceleration of the elevator when it is slowing down, as you can see by the negative slope in the graph. So in this example, we're using trial number 4, which we believe is the most accurate of the trials. So to find the acceleration of the graph of the elevator when it is slowing down, it's basically the same as when it is speeding up. Just that this time, the net force turns out negative. For example, we can see here that the net force is 0.79 and the mass is 1.27 kilograms. The net force, of course, being in newtons. When you divide the net force, negative 0.79, by the mass, 1.27 kilograms, you get 0.622 meters per second, which is the acceleration of the elevator when it is slowing down. Emphasis on the point that the acceleration is negative. And then again, emphasis on the point that this is the acceleration of the elevator when it is slowing down, so please don't be confused.
Now, Captain Foyce will present the analysis. Captain Foyce!
Whoa, sorry about that. I thought I saw Schrader there for a second. You can never be too sure about that guy. He's always after information. Anyways, the analysis of the data. The formula for finding the acceleration was simple, yet long. First, we had to find the net force. What we did was subtract the maximum force with the force exerted by the scale going up the elevator when it was at rest. After that, we divided that net force with the total mass of the weight. With that, we found the acceleration of the elevator when it speeds up. To find the acceleration of the elevator when it's slowing down, the process is similar. We subtract the minimum force exerted by the scale with the normal force being at rest or at constant speed. Obviously, you're going to get a negative number. You divide that number with the mass and you get the acceleration. Only this time it's going to be a negative number since the elevator is slowing down. The average acceleration for the trials when going up was 0.56 meters per second. The average acceleration of the trials when slowing down was negative 0.655 meters per second. We were right in guessing that the force required to accelerate different masses at the same rate would be different according to the mass. The reason is because objects with more mass have more inertia, making it harder to accelerate them. That is why, when looking at the graph, one can see that the changes are more drastic as the mass increases.
Sources of error. In trial number 4, no data was received during the first acceleration, making it impossible to analyze it. This error seems to be caused by faulty equipment. We could have also done more trials to have more accurate data.